Hi, my name is Lillian Wilson-Waite, and today I'll be discussing Lab 3. So in this lab, we were tasked with using the observations we looked at in a star's orbit of a black hole to find the mass of the black hole. Now in the past, we've predicted an object's motion by knowing factors about it and its surroundings, but now we have to use what we know about the motion itself to find out more about the surroundings. So to start off, from Newton's second law, we know that the net force is equivalent to the rate of change of momentum, dp over dt. And we also know that in this lab, the gravitational force from the black hole is the only force actually acting on the star. So F net just equals Fg, that gravitational force. Now we also want to know about the, we want to understand the parallel and perpendicular components of force. So to calculate F net, we can also just take the parallel component of net force and add it to the perpendicular component of net force. Same concept for the rate of change of momentum. And since F net and dp over dt are equivalent, the parallel component of dp over dt will be equivalent to the parallel component of net force, and same thing for the perpendicular components. So once we've found that net force, all we're going to have to do to find the mass of the black hole is plug in our data to Newton's universal law of gravitation. Now to look at the computational model, I first changed the initial conditions, inputting my email address, the star's mass, the constant g, the time step, and then the position of the black hole. And at each new data point, the code runs through a calculation loop. First, the initial velocity vector, which is the final velocity from the last point, and the final velocity vector are defined. The star's initial and final momentums are then derived from just multiplying the star's mass by the velocity vectors. And then we then find the change in momentum and the change in velocity at the given points just by finding the difference between the final and initial values. And then we find the change in momentum with respect to time by dividing the change in momentum by the change in time. So according to Newton's second law, like we just saw, the net force is equivalent to delta P over delta T, so we have just calculated the net force and can define it to make our code more coherent. Later, I also set my F-net parallel and perpendicular components equals to the parallel and perpendicular components of dp over dt since they are the same value. So once we found the net force, which is equivalent to the gravitational force on the star, we can use Newton's universal law of gravitation to solve for the black hole's mass. If we rewrite the law, the mass can be found by finding the net force times the radius squared divided by the constant g times the star's mass. Once my model has finished running, I can see that the mass of the black hole is approximately 7.24 times 10 to the 34 kilograms. So to further examine some questions this lab poses, let's look more closely at the relationship between net force and the rate of change of momentum. These two values are equivalent and their perpendicular and parallel components are equivalent as well. However, while they are equal in value, they have different meanings. The net force is equivalent to all the forces acting on the object. Every push and pull in the parallel and perpendicular direction is taken into account when we calculate F-net parallel and F-net perpendicular. However, with dp over dt, the parallel component represents the rate of change at which the object is changing speed, and the perpendicular component represents the rate at which the object is changing direction. So while the values are equivalent and they can be used interchangeably in equations, they have a different meaning, and it's important to understand that difference in meaning when we're looking at our system. Next, we were asked if it's possible for us to find a value for the mass of a new black hole that is different from the mass you found for the original one. So the answer is no, because like the question states, the motion of the observed star remains unchanged. So if the motion of the star is unchanged, that means the same quantitative amount of force is acting on it. So for the same amount of force to be acting on it, we already know that the constant g, the mass of the star, and the radius are still the same. So the mass of the black hole must remain unchanged as well for the net force and the motion, therefore, to be unchanged.